Hello decathletes, and welcome to the 5th Decademy Mathematics video lecture. In this video, we'll learn about arithmetic and geometric series, so let's get started. A series is merely the sum of a sequence. The reasoning behind wanting to find an easy formula for finding a series is best illustrated by the story of little Carl Gauss, but it does have practical applications in the development of integral calculus and, well, statistics. The lesson we get from the Gauss story is that a simple algorithm to find the sum of an arithmetic sequence is to pair up the smallest and largest values, then the next smallest and next largest, and so on. Because of the common difference, these pairs all have the same sum. Now, if we have an even number of values, we can pair things up easily to get x sub 1 plus x sub k times k over 2, which is the sum. This is because x sub 1 plus x sub k is the value of the sum of the pairs, because each pair has the same sum. This is the value for each pair. K over 2 is the number of pairs you get. Now, what if we have an odd number of values? Well, since this is an arithmetic sequence, it's easy to find the next term and give ourselves an even number again. So the sum of this would be x sub 1 plus x sub k plus 1, we're adding a term on the end, times k plus 1 over 2. However, since we added a term, we need to subtract that last term in order to find the sum of our odd numbered sequence. So k plus 1. Now, because this is an arithmetic sequence, we have a direct formula for each of these terms. So if we substitute those in, we get a plus k plus 1 minus 1 times d times k plus 1 over 2 minus a plus k plus 1 minus 1 d. We can simplify this a little bit to get 2a plus kd times k plus 1 over 2 minus a plus kd. We can put this all over the same denominator now. So 2a plus kd times k plus 1 minus 2a minus 2kd, because we put that second half all over 2. So let's rewrite that on the new slide. 2a minus plus kd times k plus 1 minus 2a minus 2kd all over 2. Let's distribute the k plus 1 now to get 2a k plus 1 plus kd k plus 1 minus 2a minus 2kd all times 1/2. We can now factor. So if we take this and this, we get 2a k plus 1 from there. We took a 2a out of here, so that leaves us with negative 1. Plus, we can also factor these. kd. We get a k plus 1 and a minus 2. This is all still over 2. So that's k minus 1. So now we have 2ak plus k minus 1 times kd all over 2. We can factor out a k from both of these to get 2a plus k minus 1 d times k over 2. This can be split up into a plus k minus 1 d times k over 2. And now we go back to our direct formula, and we see a is the same as x sub 1, a plus k minus 1 times d, is the same as x sub k times k over 2. And it's the exact same formula. It's not immediately obvious that this should be the case. After all, when k is odd, k over 2, this is a fraction. But the sum is certainly not going to be a fraction. This means that this part right here must be even. And so we look at where we had that. We had that right here. Well, 2a is clearly going to be even. It's 2 times the number. And this part right here, since k is odd, then k minus 1 must be even. So this part's even as well. An even number plus an even number is also an even number, so we will not end up with a fraction. Well, what about a geometric series? Here we can't do the same kind of pairing because there's no common difference between the values. If we want a trick, we'll have to exploit the common ratio. So let's take a look at a general geometric sequence. The first term is a. The second term is a times r, then ar squared, and so on. ar to the k minus 1. So, let's say this is our sum. What happens if we add another term on? So now we have a plus ar plus ar squared plus dot 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 plus ar k minus 1 plus ark. Well, this would equal our sum plus ark. Now let's take this first term and bring it over. Subtract it from both sides. So we have ar plus ar squared plus dot 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 ar k minus 1 plus ar to the k equals our sum plus ar k minus a. Now here we could factor out an r from each term. So let's do that. R a plus ar plus dot 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 plus ar k minus 2 plus ar k minus 1, which still equals the same thing. Well, if we look at this, this is our sum. You notice these are the same value. So we can rewrite this. R times S equals S plus ar to the k minus a. So now we can subtract s from both sides. So we have rs minus s equals ar to the k minus a. So this is sr minus 1 equals ark minus a. So our sum is equal to a, which we factor out of the top, rk minus 1 over r minus 1. This means, however, that our ratio, the common ratio, cannot equal 1, or else we get a 0 in the denominator, and we can't have that. So how would we find the sum of a geometric sequence where the common ratio is 1? Well, let's take a look at such a sequence. The first term would be a. The second would be a times r. The ratio is 1, so it would be a. The third term would be a times r squared. Well, r squared is still 1, so that'd be a. And so we see that this is a plus a plus a added to itself k times. The sum is a times k. You could also use the algebraic series formula, since with a common ratio, the sequence has a common difference, d equals 0. Now we can also find an infinite series, but this is usually pretty useless. The infinite series of any arithmetic sequence is either going to be infinity or negative infinity, because you're adding up numbers with a common difference, so you'll either get really big or really small. And infinite geometric series are also sometimes going to be positive infinity or negative infinity. But there is a special kind of geometric sequence, and that is if the values of the sequence get closer and closer to 0. For example, take the sequence 1, 1/2, 1/4, 1/8, 1/16. In this case, the infinite series will actually be a number. In order for something like this to happen, though, the ratio must be less than 1. So, in this case, it's a, which equals 1. So we have 1 times the ratio, which is 1/2 to the k minus 1. So when k is 1, it's 1/2 to the 0, which is 1. When k is 2, this is 1/2 raised to the first power, 1/2 raised to the second, to the third, and so on. So let's take a look at the formula for a finite sequence. We have the sum equals a rk minus 1 over r minus 1. Well, if you're familiar with calculus or limits, you might notice that as k reaches infinity, this will go to 0. And this is because r to the k, when k is smaller, this value will get exceedingly small. You can see that here. It'll keep going on 1/32nd, 1/64th, and so on. It's going to get extremely small. So when k is infinity, that's actually going to become 0. So what we can do is, for an infinite series, we can get rid of this because it will be 0. To get s equals a times -1 over r minus 1. However, we normally rewrite this as a over 1 minus r. And so this is the formula for an infinite series. So now we know how to find the sum of finite arithmetic and finite geometric sequences, known as the finite arithmetic series and the finite geometric series. And we also know how to find certain infinite geometric series. In the next video, we'll introduce sigma notation.